Hello, I'm Robert, and I'm going to show you a simple experiment in artificial gravity which you can do at home. And this is to test ideas which could help with solve problems with zero gravity and also make interplanetary spaceflight easier to do. The background to this is that NASA have guidelines that's a maximum of 3 rotations per minute for artificial gravity, and that's if you want an hour of artificial gravity. And then when you have longer periods of time, then this goes down to a fraction of a rotation per minute if you want to spend days and years. These guidelines, they go back to the 1970s, and they're the reason why in the early 1970s designs for space stations, why they're so big. So the idea of the Stanford Torus, a huge space station, kilometre scale space station, and also the O'Neill cylinders, and that's so you can have these slow rotation rates and still have full gravity. Then the only way you can get full gravity is by increasing the diameter. However, nowadays we're looking at this in a different way. To start with, you can go back and look at the original experiments. You actually find that different experimenters have conflicting ideas and suggestions, so some of the papers say some things and some say other things. But the other thing is it makes a big difference whether you're looking at the reason why you want the gravity. So do you want to be able to have fine control and just go around your ordinary everyday life? Or do you just want to be there for a short period of time, and it's okay are you just wanting to be able to withstand nausea? Is it okay also if you can keep your head fixed in position, you can withstand a much faster spin rate? And if the only problem is nausea, then you can also withstand a much faster spin rate. And just a slight increase in spin rate can make a huge difference. So if you can go from 3 rotations per minute to say 30 rotations per minute, then that gives 100 times the amount of artificial gravity, because it goes up by the square of the velocity. And we have a different idea now about why we would be using, especially the short-arm centrifuges. And short-arm centrifuges are very much like a kind of medicine. And that's the reason why we'd be using it. It's like a kind of medical treatment that you go into your short-arm centrifuge. And it's to deal with when astronauts go into space, and actually technically within a few hours and within a day or two, they are actually what you would, if they're the same symptoms on the Earth, you would say this is one sick astronaut. So the red blood cell count goes down by 10%, the resting heartbeat increases, the liver and the kidney don't function properly, they no longer digest food quite as well as before, they become dehydrated, they find it harder to drink adequate amounts of water, and loss of magnesium, they can't lose heat because the convection, they no longer have the convection you get in normal gravity, and so sweat a lot more. And if you looked at them and you saw them as a patient on the Earth, then apparently you would think this is one sick astronaut, losing bone loss several percent per month it can be. And but this is a sickness which is very easily cured. So the Soviet astronauts, and the cosmonauts as they called them, then towards the end of their visits, if they were the only ones who've done long duration space flights are the Russians. The Americans haven't done very long duration space flights yet. And after a year in space, some of them got very ill. There was one case of one of the early cosmonauts. He became so ill that they didn't think it was safe for him to pilot his capsule back to the Earth. They sent another cosmonaut to join him for the last few months, and then sent a third cosmonaut. At the usual exchange of crew, they took the very unusual step of one of the crew, he just went up and immediately came back down again to pilot this sick astronaut back to Earth. But he recovered very quickly. When you first land on the Earth, you are as weak as a baby. You have to be carried off your spaceship. But within a few hours, then you're able to stand up and walk around. So that's very astonishingly quick. And then within a couple of months, then you're back to normal health, pretty much. The only thing left to recover are your bones, and these recover over a longer period of time, the harder outside of your bone, then that recovers to its normal density after 2 years. And then the inner spongy part of the bone, then that recovers over a longer period of time. So you're pretty much recovered after 2 years, and you're very close to recovered after a couple of months after long duration spaceflight. So the gravity medicine is very effective. You don't need to worry too much. The only thing with long-term problems is problems with your eye. Apparently there's been one case where someone had long-term issue with the eye as a result of their zero gravity space flight. In most cases that also recovers. So you have problems with blurry vision in your eye. And so that's the medicine of gravity. This leads to the idea that if you're using it as medicine and you're talking about the possible maximum lifespan in space of 2 years under zero gravity. Now, if you would just extend that, say to 10 years, so the maximum lifespan is 10 years. Of course, it's not based on any actual data. Nobody has actually died in space of zero gravity. It's very easy to return them to the Earth. So if you start getting very sick in space, you can be returned to the Earth. But if you're out at Mars and you get very sick, you can't be returned to the Earth. So this leads to the idea that of using gravity as a medicine, not necessarily fully restoring you to the normal Earth conditions, but just to extend your lifespan in space. This could make it possible, so if your maximum lifespan is say 10 years in space, then it would be easy to go out to Mars, spend a few years orbiting Mars, and come back to Earth. And it would also mean that it would be very easy to have, for instance, a space station in the L1 and L2 positions, the near side and the far side of the Moon. And in these positions, it's a little bit like geostationary orbit, that if you go to the far side of the Moon, you have the balance of the gravity of the Earth and the gravity of the Moon. It keeps you hovering above a fixed spot, the far side of the Moon. And there's also one on the near side of the Moon, and it's very close to the Moon. It keeps you hovering above the near side of the Moon due to the balance of the gravity of the Earth and the Moon. And I could go into that a little bit more later on. So there's certainly astronomers and mission specialists have been very interested in the idea of a space station in the L1 and L2 positions. If you could live there for years at a time, then you wouldn't need to keep resupplying it from the Earth. That could make quite a difference to the cost of keeping a human presence up there. It would be very useful for exploring the Moon. You could explore the Moon by remote telepresence. So this idea of gravity as a medicine, then you get the idea that just an hour of gravity a day, or even just a few minutes, might make a huge difference. And then you go and re-examine these things, and you're now no longer thinking in terms of being able to just do your normal activities. All you want to be able to do is either maybe some exercise for a short period of time, or you maybe want to sleep or just rest under ordinary gravity, or maybe digest your meal under ordinary gravity. So when you think about it in those terms, then you look back at the experiments, and they say, for instance, that if your head is fixed in position, this greatly reduces the symptoms. And then if you're looking at nausea, rather than just the fine hand-eye control, you can tolerate much faster spin rates. Then, as well as that, the early experiments, they didn't look at the possibility of adaptation. And then finally, also, the early experiments, their aim was to try and find something that everyone can tolerate. And there's a great deal of variance, individual variance, in what you can tolerate. So if this would greatly reduce the cost of an interplanetary spaceflight and make it much easier to have interplanetary spaceflight and going to the far side of the Moon and things like that, then that could be like sailors. So if you are designing a cruise ship, you want a cruise ship that hardly moves at all in the water, because you're designing it so that everyone is able to sail in it. But if you're designing a trawler, then this is for sailors, and the sailors are going to be able to withstand rocking about. And you look at films of trawlers, they go back a huge amount of rocking back and forth in rough seas, and the sailors don't become seasick, and they can tolerate that. So if you're designing it around sailors, you don't need a big thing as pretty much flat in the oceans. It could be very much the same in space, that your interplanetary space flight would be done by astronauts who are able to tolerate high spin rates for artificial gravity. So there are all these ideas suggesting that maybe a very high, fast spin rate could be quite suitable depending how you're using your artificial gravity and how long you're spending it, and whether it's for sleeping or just exercise or doing normal activities. And so anyway, that's what this experiment is all about. And there's quite good evidence from your ordinary experience. There's an amusement park ride which involves, it's called Gravitron, and it has a spin rate of 24 rotations per minute. So that's very fast, far, far above the NASA guideline, and ordinary people can manage finding this at least for a few minutes. And then you might wonder, well, what about an hour at this 24 rotations per minute? So the MIT, they did a study quite recently, and they had young students, and they spent an hour each day for 5 days, and they were looking at whether you could adapt. And so to start with, there's quite a lot of discomfort at 23 rotations per minute and not very good coordination, but after 5 days there's a very dramatic improvement, and so they adapted very quickly to these 23 rotations per minute. So just doing 1 hour and then another hour the next day, another hour the next day, and by 5 days they had a huge improvement in their ability to deal with these conditions. And at the end of that paper, they say it's high time that we sent a centrifuge in space because conditions are so different in space. And then other ordinary experience, then a Muslim friend of mine, he suggested, take a look at the whirling dervishes. And so the whirling dervishes, they spin around, and I had to look at the video of them. You can find videos on YouTube, and they spin around at getting on for 40 rotations per minute, and they do that in the ceremony that I looked on YouTube. It was for about half an hour that they were spinning at 40 rotations per minute. So this is another thing, it's really suggesting that you can adapt and tolerate really quite high spin rates. So it might well be that as you go on over, if you're doing it every day, 1 hour a day, and as time goes on, you might be able to tolerate, and maybe even for hours at a time, if you spend lots of time in space. And so that leads to this experiment that you can try for yourself at home and see how you are. And you might find some people are very susceptible to this, and they just can't tolerate it at all. And so they would take a long time probably to adapt. And so there's a program very popular here in United Kingdom, Strictly Come Dancing. And in this program you have celebrities, and then you have professional ballroom dancers, and then some of the celebrities, every year you have 1 or 2 of the celebrities who really can't tolerate the spins that you do in the waltzes and some of the dances like that. And then gradually adapt to it. So even just a few spins, then some people can find that quite problematical. At the other end, then you get ice skaters, and over years they adapt to very, very fast spin rates. And the very fastest spin rates you can tolerate are into multiple spins per second. And the fastest, the Guinness Book of Records, is 308 spins per second, which they can do without any nausea. They might feel a little bit dizzy as they come out of the spin. During the spin they're not dizzy either, but as they come out of it they feel a little bit dizzy and giddy, but obviously you're able to maintain coordination. You've seen them in the Olympics. So this shows you can actually tolerate very, very fast, far, far beyond what we need for artificial gravity, if you adapt to it over a long period of time. Anyway, we're not going to be going at multiple spins per second. In this one, we're just going to be doing 1 spin every 2 seconds. This gives you 30 rotations per minute. So this is how you do it. But then it's easiest if you have a metronome going. And so if you've got a metronome, you can set it to 1 click per minute, 1 click per second, so that's 60 beats per minute. And it's very helpful if you have 2 tick sounds, so tick, tock, tick, tock. I'll just simulate the metronome, so I don't need to go and switch it on. So you will go around and you go before I start this experiment, before you start the experiment, be aware that everything is going to go blurry. So as you start spinning around, you won't be able to see things clearly. And you might well fall over just because you can't see clearly. And you might get a bit dizzy or giddy. So when you first start, and then when you stop, you will feel giddy when you stop, for a second or two at least. So make sure that you're in a situation where it doesn't matter if you fall over. So some walls in all directions when you first try, or something you can grab a hold of, or something very soft to land on all around you in case you fall over when you first try it. Or else try very, very slow spin rates to start with. And then when you're spinning, expect everything to go blurry. And that doesn't mean that you're dizzy just because it's gone blurry. You won't be able to see your surroundings when you're spinning, even as slowly as 30 rotations per minute. It is quite a slow spin rate, so this is what it's like. Tick, tock, tick, tock, tick, tock, tick, tock. And then spinning, as when you want to stop, then gradually slow down very gradually, and then you're much less likely to fall over. So that's the experiment, very simple experiment. And then the question is, how much of that can you tolerate? And you might find that even the amount I did just then was enough to make you even maybe feel a bit nauseous already. Or you might find that you could just keep on going on and on and on. And that's actually what I found when I first tried that. So I'm sure there's a probability distribution with a tail, and there's probably a tail that way where people are very susceptible, and the other way people are not susceptible at all. And when I tried that, and the first time I managed 10 to 20 minutes, I can't remember what it was. Second day I did 30 minutes, and then the third day I did an hour, and I felt I could have kept going. I just stopped after an hour because that was my objective, to do an hour, same as the MIT experiments. So, and I did feel, in that 1 hour, in the middle at one point I felt a little bit sick, but then it went away as I continued spinning. When I stopped, then I felt momentary, just for a few seconds, a little bit sick, and it went away very quickly. And I'm sure I could have kept going for a couple of hours, or certainly well over an hour. So at least some people can spin around, just from my own experience. And this is equivalent to having your head fixed in these experiments, because your head is fixed as you turn around. Now, something that might be a bit disconcerting is the way that everything goes blurred as you turn around. In the gravitron, you're in an enclosed environment. So if you do find that you're very susceptible, it still is possible that you might find it much easier if your surroundings were enclosed, so you don't actually see the blurry sensation as you spin around. Anyway, so that's the experiment, and now I think hopefully I'll have a little bit of time in the rest of this video to talk just a little bit about how I would whether you could put that into the ISS. So once we start talking about 30 rotations per minute, then that requires a very, very small centrifuge in order to get full gravity. A very simple calculation, rather nice, neat calculation, is that it's a rather nice coincidence. If you have a 1 meter centrifuge, then, and if you go at 30 rotations per minute, so that's a rotation every 2 seconds. So you have the velocity, you get 2 pi r for the circumference divided by the time of 2 and the radius 1, so 2 pi times 1 divided by 2, you get pi as the speed. So you have pi meters per second. So that's 3.14 meters per second for the spin around. That's the speed at which your hand would be going if your hand is a meter away at 30 rotations per minute. And so then, if you try and work out what the acceleration is, then the formula is v squared over r. The velocity we've already got is pi. Take its square, the radius is 1. And it turns out that the square of pi is a very good approximation for the acceleration due to gravity, just by coincidence. It's 9.8 something, and the acceleration due to gravity is also 9.8 something meters per second per second. So this means that if you're spinning at 30 rotations per minute with a 1 meter radius, then that gives you, it's actually very slightly over full gravity in your centrifuge. If you spin at a rather slower rate of 23 rotations per minute, that's 60% of gravity. So, and if you spin less and less, then it'll be less gravity. It's because it's the square, then just a small reduction greatly reduces the amount of gravity. So that's, again, at least the idea. Could we send something like this up in space? A 1 meter radius centrifuge. So it said at the end of that paper, the MIT paper, it's high time we put something into space. How about actually sending something into space? And so at first I was quite optimistic about this. Well, first of all, let's describe the thing that we would send into space, and then ask whether we can put it anywhere. First I was very optimistic. Now it turns out there's some problems with the idea of trying to fit it into the ISS. But the actual thing that you would send into space could be very lightweight construction. So I'm thinking about basically a hammock. You don't need a big heavy centrifuge in space. You don't need a horizontal arm. There's no gravity pulling downwards or pulling at right angles to the arm. All you need is to be able to suspend, and it doesn't need to be able to support hypergravity either. All the Earth-based centrifuges have to be able to support hypergravity. But this, it only needs to be able to support ordinary Earth gravity. And that means that anything that could suspend a normal hammock, for instance, would be a strong enough construction for your centrifuge. And then also the speeds at which you're moving. When you're talking about such a short arm as 1 meter, then that's pi meters per second. This is really not very fast. Think, I mean, look at how fast my hand's going around. It's not going that fast. And then if you actually do the calculation and you look at the speed, for instance, the Skylab astronauts when they were jogging around in Skylab, then I worked it out as roughly 18 meters circumference and took about 5 seconds to go around. It's 3.6 meters per second, so that's more. So this is less than the jogging speed of the Skylab astronauts when it's jogged around the inside of Skylab 1. Which, by the way, is the only thing we have that is a bit like artificial gravity in space. And they had half gravity at their feet, they had a fifth gravity at their heads, and it wasn't an experiment, it was just them doing recreation, and they did it for half a minute of 12 rotations per minute. So we know for sure that you can withstand half a minute of 12 rotations per minute. I suppose that's about our only data point for humans in centrifuges in space. And they had no obvious ill effects from that. So anyway, this is a very slow speed. It's actually rather similar. If you look at the way the astronauts, when they push themselves, they launch themselves from one place to another, and it's almost like swimming, going through the interior of the ISS. It's a sort of push, and they just sort of, like diving, they sort of glide from one place to another. Then they go to getting on for this speed as well. So that seems seems then like a very safe thing. You don't need to have a massively engineered centrifuge, and just something like a hammock going at this speed, very much almost like the experiments they do spinning water bottles in the ISS. If they had enough space in there to fit a 2 meter diameter centrifuge, then it would be a pretty easy experiment to do, and it wouldn't be need to be very heavy. Now, the problem is that the inside of the ISS is it's very frustrating, because the modules of the ISS, they actually form, nearly all the modules are over 4 meters in diameter, which will give you plenty of space to fit in a 2 meter diameter centrifuge. But the problem is, of course, that first of all, they've put stuff in between, they've squared it off on the inside, and then they've put loads and loads of experiments, and so you have a whole thickness of experiments along all the walls of the ISS in all the modules. And then you have exercise machines, and about the only place where you have any space at all are like areas where they make their tea or they have their meals, where they probably wouldn't look too kindly to putting up a centrifuge in there. And in any case, it's not really quite big enough. Even these areas, then they're not quite big enough to fit a 2 meter diameter centrifuge comfortably. I also had to look at the cupola, and it's almost big enough, but there's not very much space between the cupola. That's the big window that the astronauts look out of. There's not much space between that and the main body of the ISS. So I don't know, maybe someone else might like to have a look at the plenty fly-throughs of the ISS and see if you can see any way they could be fitted inside. If there was some way of fitting it inside the ISS, then you could actually submit it. There's a proposal for NASA have put out a request, a public request for anyone, non-partner program. It's their non-partner program, and they're requesting for proposals for experiment to be sent to the ISS. And the deadline is in May. So you've only got a couple of months, so you would have to get a move on very quickly to meet this particular one. But if we could find some place to put it in the ISS, and this was an experiment that could be put anywhere in the ISS, if we could find a place to put it in the ISS, maybe we could persuade NASA to actually fly it and try it out. But as far as I can see, you would have to get them to rearrange the interior of the ISS. That seems a little bit, I don't know how possible that is, in order to make space for it. They certainly have big things, as big as this. They have the zero gravity exercise machine, and in the place where they have the big zero gravity exercise machine, that's almost enough space for this as well, if you kind of organised it properly. Then the other possibility with the ISS is that they're planning to fly a Bigelow inflated habitat, and this is going to be 3 meters diameter, over 3 meters diameter, and getting on for 4 meters in length. And it mightn't have very much inside, just some monitoring equipment to try and work out how well the inflatable habitat performs. So maybe if you could organise the interior of that, there might be just enough space to fit in a short-arm centrifuge. If we could somehow persuade the people who are planning it, I'm sure once it's up there, and it would start filling with clutter, and you wouldn't be able to fit it in. But maybe if you can get it in at an early date, and design it around having a short-arm centrifuge inside it, there's certainly plenty enough diameter for it, if you're just talking about a 2-meter centrifuge. So that's, anyway, whether it's possible enough, let's start thinking about the details of how the centrifuge might work. So, as I say, I'm thinking about something very lightweight, and it would be just like a central pole, and suspending it from that you have your hammock, but not with kind of ropes like a normal hammock, but with something more rigid so it can be spun around, and also to hold it extended so that you're in zero gravity, because you're in zero gravity, easy to get in, and it doesn't just kind of collapse around you. And then you have a lightweight motor at the pivot, at the axle, and this would be enough to set it spinning, and then it would gradually go faster and faster. It doesn't need to be a very strong motor. And then for safety reasons, this motor would be designed so that if you reach out and touch something, for instance, then, and so that you're stopping the spin, or you bump into something, there's some obstruction or whatever that you didn't expect, then it's just like running into a wall or something. Then if for safety reasons, it's not going to happen in normal situations, but just for safety reasons, then the motor would immediately cut out, or it might even assist the braking. So that's my idea there. Now there would be 2 ways you can be orientated relative to the axle. And if you imagine, for instance, if they could find space for it inside the ISS somewhere, then normally it's kind of squared off. So you have a ceiling and a floor, and then 2 walls. Let's arbitrarily call one of the walls the ceiling. Of course, there's no direction, because